I'm back. Let me continue with the book at chapter 6.8 Unions. A union is a variable which may hold at different times objects of different types and sizes, with the compiler keeping track of size and alignment requirements. Unions provide a way to manipulate different kinds of data in a single area of storage without embedding any machine-dependent information in the program. As an example, again from a compiler symbol table, suppose that constants may be ints, floats, or character pointers. The value of a particular constant must be stored in a variable of the proper type. Yet it is most convenient for table management if the value occupies the same amount of storage and is stored in the same place regardless of its type. This is the purpose of a union: to provide a single variable which can legitimately hold any one of several types. As with views, the syntax is based on structures. The variable uva1 will be large enough to hold the largest of three types regardless of the machine it is compiled and the code is independent of hardware characteristics. Any one of these types may be assigned to uva1 and then used in expressions, so long as the usage is consistent. The type retrieved must be the type most recently stored. It is the responsibility of the programmer to keep track of what type is currently stored in a union. The results are machine dependent. If something is stored as one type and extracted as another, syntactically members of a union are exist as like this or like this. Just as for structures, if the variable uType is used to keep track of the current type stored in uva1, the one might think code such as like this. Unions may occur within structures and arrays and vice versa. The notation for existing a member of a union in a structure, or vice versa, is identical to that for nested structures. For example, in the structure array defined by like this, and the first character of the string pva1 by. In effect, a union is a structure in which all members have offset 0. The structure is big enough to hold the widest member, and the alignment is appropriate for all of the types in the union. As with structures, the only operations currently permitted on unions are accessing a member and taking the address. Unions may not be assigned to passed to functions or returned by functions. Pointers to unions can be used in a manner identical to pointers to structures. The storage allocator in Chapter 8 shows how a union can be used to force a variable to be aligned on a particular kind of storage boundary. 6.8 Typediff. C provides a facility called Typediff for creating new data type names. For example, the declaration makes the name length a synonym for int. The type length can be used in declarations, casts, etc. in exactly the same ways that the type int can be. Similarly, the declaration makes string a synonym for char, asterisk for character pointer, which may then be used in declarations like. Notice that the type being declared in a type div appears in the position of a variable name, not right after the word type div. Syntactically, type div is like the storage classes extern, static, etc. We have also used uppercase letters to emphasize the names. As a more complicated example, we could make type div for the three nodes shown earlier in this chapter. This creates two new type keywords called tree_node, a structure, and tree_ptr, a pointer to the structure. Then the routine dialog could become like this. It must be emphasized that a type div declaration does not create a new type in any sense. It merely adds a new name for some existing type. Nor are there any new semantics. Variables declared this way have exactly the same properties as variables whose declarations are spelled out explicitly. In effect, type div is like hash define, except that since it is interpreted by the compiler, it can cope with textual substitutions. It can cope with textual substitutions. That are beyond the capabilities of the C macro preprocessor. For example, type div int creates the type PFI for pointer to function return int, which can be used in contexts like the sort program of chapter 5. There are two main reasons for using type div declarations. The first is to parameterize a program against portability problems. If type divs are used for data types which may be machine dependent, only the type divs need change when the program is moved. One common situation is to use type div names for various integer quantities, then make an appropriate set of choices of short, int, and long for each host machine. The second purpose of type divs is to provide better documentation for a program. A type called tree_ptr may be easier to understand than one declared only as a pointer to a complicated structure. Finally, there is always the possibility that in the future the compiler or some other program such as int may make use of the information contained in type div declarations to perform some extra checking of a program. Chapter 7, Input and Output. Input and output facilities are not part of the C language, so we have de-emphasized them in our presentation thus far. Nonetheless, real programs do interact with their environment in much more complicated ways than those we have shown before. In this chapter, we will describe the standard iNaturalist library, a set of functions designed to provide a standard iNaturalist system for C programs. The functions are intended to present a convenient programming interface, yet reflect only operations that can be provided on most modern operating systems. The routines are efficient. The routines are efficient enough that users should seldom feel the need to circumvent them for efficiency, regardless of how critical the application. Finally, the routines are meant to be portable, in the sense that they will exist in compatible form on any system where C exists, and that programs which confine their system interactions to facilities provided by the standard library can be moved from one system to another essentially without change. We will not try to describe the entire iNatural library here. We are more interested in showing the essentials of writing C programs that interact with their operating system environment. Seven point one. Access to the standard library. Each source file that refers to a standard library function must contain the line near the beginning in the file studio.h defines certain macros and variables used by the iNatural library. Use of the angle braces instead of the usual double quotes directs the compiler to search for the file in a directory containing standard header information. On Unix, typically as user/include. Furthermore, it may be necessary when noting the program to specify the library explicitly. For example, on the PDP-11 Unix system, the command to compile a program would be like this. Yeah. Hang on. Would be like this, where the middle score ls indicates loading from the standard library. The character L is the letter L. Of course, I know it's not 1, it's L. 7.2 Standard input and output, getchar and putchar. The simplest input mechanism is to read a character at a time from the standard input. Generally, the user's terminal with getchar. Getchar returns the next input character each time it is called. In most environments that support C, a file may be substituted for the terminal. A file may be substituted for the terminal by using the angle bracket convention. If a program proc uses getchar, then the command line causes proc to read in file instead of the terminal. The switching of the input is done in such a way that proc itself is obvious to the change. In particular, the string angle in file is not included in the command line arguments in argv. The input switching is also infeasible if the input comes from another program via a pipe mechanism. The command line runs the two programs, other prog and prog, and it arranges that the standard input for prog comes from the standard output of other prog. GetChar returns the value EOF when it encounters end of file on whatever input is being read. The standard library defines the symbolic constant EOF to be -1, with a hash defined in the file still pointH, but tests should be written in terms of EOF, not -1, so as to be independent of the specific value. For output, putChar puts the character C on the standard output, which is also by default the terminal. The output can be directed to a file by using angle bracket if prog uses putChar. We'll write the standard output into out files instead of the terminal. On the Unix system, a pipe can also be used. Puts the standard output of prog into the standard input of other prog. Again, prog is not aware of the redirection. Output produced by printf also finds its way to the standard output, and calls to putChar and printf may be interleaved. A surprising number of programs read only one input stream and write only one output stream. For such programs, isNatural with getChar, putChar, and printf may be entirely adequate, and is certainly enough to get started. This is particularly true given file redirection and a pipe facility for connecting the output of one program to the input of the next. For example, consider the program lower, which maps its input to lowercase. The functions is upper and to lower are actually macros defined in std.h. The macro is the upper tests whether its argument is an uppercase letter, returning non-zero if it is, and 0 if not. The macro to lower converts an uppercase letter to lowercase, regardless of how these functions are implemented on a particular machine. Their external behavior is the same, so programs that use them are shielded from knowledge of the character set. To convert multiple files, you can use a program like the Unix Autodidactism cat to collect the files, and thus avoid learning how to access files from a program. Cat is presented later in this chapter. As an aside, in the standard isNatural library, the functions getChar and putChar can actually be macros, and thus avoid the overhead of a function call per character. We will show how this is done in Chapter 8. 7.3 Formatted output printf. The two routines printf for output and scanf for input next section permit translation to and from character representations of numerical quantities. They also allow generation or interpretation of formatted lines. We have used printf informally throughout the previous chapters. Here is a more complete and precise description. Printf converts formats and prints its arguments on the standard output under control of the string control. The control string contains two types of objects: ordinary characters, which are simply copied to the output string, and conversion specifications, each of which causes conversion and printing of the next successive argument to printf. Each conversion Each conversion specification Each conversion specification is introduced by the character percent and ended by a conversion character. Between the percent and the conversion character there may be a minus sign, which specifies left adjustment of the converted argument in its field. A digit string specifying a minimum field width. The converted number will be printed in the field at least this while, and wider if necessary. If converted argument has fewer characters than the field width, it will be padded on the left or right if the left adjustment indicator has been given. To make up the field width, the padding character is blank normally and 0 if the field width was specified with a leading 0. This 0 does not imply an octal field width. A period, which separates the field width from the next digit string. A digit string, the precision, which specifies the maximum number of characters to be printed from a string, or the number of digits to be printed to the right of the decimal point of a float or double. A length modifier L, letter L, which indicates that the corresponding data item is a long rather than an int. The conversion characters and their meanings are: the argument is converted to decimal notation, or the argument is converted to unsigned octal notation without a leading 0. X, the argument is converted to unsigned hexadecimal notation without a leading 0x. U, the argument is converted to unsigned decimal notation. C, the argument is taken to be a single character. S, the argument is a string. Characters from the string are printed until a new character is reached or until the number of characters indicated by the precision specification is exhausted. E, the argument is taken to be a float or double and converted to decimal notation of the form like this, where the length of the string of ends is specified by the precision. The default precision is 6. F, the argument is taken to be a float or double and converted to decimal notation of the form like this, where the length of the string of ends is specified by the precision. The default precision is 6. Note that the precision does not determine the number of significant digits printed in F format. G, use %E or %F, whichever is shorter. Non-significant zeros are not printed. If the character after the percent is not a conversion character, that character is printed. Thus, percent may be printed by %%. Most of the format conversions are obvious and have been illustrated in earlier chapters. One exception is precision as it relates to strings. The following table shows the effect of a variety of specifications in printing "Hello World." 12 characters. We have put columns around each field so you can see its extent. A warning: printf uses its first argument to decide how many arguments follow and what their types are. It will get confused and you will get nonsense answers if there are not enough arguments or if there are the wrong type. Exercise 7, middle score 1. Write a program which will print arbitrary input in a sensible in a sensible way. As a minimum, it should print long graphic characters in octal or hex according to local custom, and fold long lines. 7.4 Formatted input scanf. The function scanf is the input analog of printf, providing many of the same conversion facilities in the opposite direction. Scanf reads characters from the standard input, interprets them according to the format specified in control, and stores the results in the remaining arguments. The control argument is described below. The other arguments, each of which must be a pointer, indicate where the corresponding converted input should be stored. The control string usually contains conversion specifications, which are used to direct interpretation of input sequences. The control string may contain blanks, tabs, or new lines, white space characters, which are ignored, ordinary characters not present, which are expected to match the next non-white space character of the input string. Conversion specifications consisting of the character percent, an optional assignment, suppression, character asterisk, and an optional number specifying a maximum field width, and a conversion character. A conversion specification directs the conversion of the next input field. Normally, the result is placed in the variable pointed to by the corresponding argument. If an assignment suppression is indicated by the asterisk character, however, the input field is simply skipped. No assignment is made. An input field is defined as a string of non-white space characters. It extends either to the next white space character or until the field width. If specified field is exhausted, this implies that scanf will read across line boundaries to find its input. Since new lines are white space, the conversion character indicates the interpretation of the input field. The corresponding argument must be a pointer. It is required by the call by values semantics of the following conversion characters are legal. Like this. Let us just skip. The conversion characters D, O, and X may be preceded by letter L to indicate that a pointer to long rather than int appears in the argument list. Similarly, the conversion characters E or F may be preceded by L to indicate that a pointer to double rather than float is in the argument list. For example, the call with the input line will assign the value 25 to I, the value 5.432 to X, and the string something properly terminated by /0 to name. The three input fields may be separated by as many blanks, tabs, and new lines as desired. The call like this with input like this will assign 56 to I, assign 789.0 to X, skip over 0, 1, 2, 3, and place the string double quote 4 or 5 in name. The text call to any input routine will begin searching at the letter A. In these two examples, name is a pointer and thus must not be preceded by a ampersand. In another example, the rudimentary calculator of chapter 4 can now operating with scanf to do the input conversion. Like this code. Scanf stops when it exhausts. Scanf stops when it exhausts. Scanf stops when it scanf stops when it exhausts its control string, or when some input fails to match the control specification. It returns its values in number of successfully matched and assigned input items. This can be used to decide how many input items were found on one end of file EOF is returned. Note that this is different from 0, which means that the next input character does not match the first specification in the control string. The next call to scanf resumes searching immediately after the last character already returned. A final warning: the arguments to scanf must be pointers. By far, the most common error is writing instead of 7.5 in-memory format conversion. The functions scanf and printf have siblings called scanf and sprintf, which perform the corresponding conversions but operate on a string instead of a file. The general format is like this. Sprintf formats the argument in arg1, arg2, etc. according to control as before, but places the result in string instead of on the standard output. Of course, string had better be big enough to receive the result. As an example, if name is a character array and n is an integer, then like this creates a string of the form temp n in name, where n is the value of n. Scanf does the reverse conversions. It scans the string according to the format in control and places the resulting values in arg1, arg2, etc. These arguments must be pointers. The call, like this, sets in to the value of the string of digits following temp in name. Exercise 7 middle score 2. Rewrite the desk calculator of chapter 4 using scanf and or scanf to do the input and number conversion. 7.6 File exists. The programs written so far have all read the standard input and written the standard output, which we have assumed are magically predefined for a program by the local operating system. The next step in snashell is to write a program that accesses a file which is not already connected to the program. One program that clearly illustrates the need for such operations is cat, which concatenates a set of named files onto the standard output. Cat is used for printing files on the terminal and as a general-purpose input collector for programs which do not have the capability of accessing files by name. For example, the command prints the contents of the file x.c and y.c on the standard output. The question is how to arrange for the named files to be read, that is, how to connect the external names that a user thinks of to the statements which actually read the data. The rules are simple. Before it can be read or written, a file has to be opened by the standard library function fopen. Fopen takes an external name, like x.c or y.c, does some housekeeping and negotiation with the operating system, details of which needn't concern us. Hang on. I'm sorry. What happened? Does some housekeeping and negotiation with the operating system, details of which needn't concern us, and returns an internal name which must be used in subsequent reads or write of the file. This internal name is actually a pointer called a file pointer to a structure which contains information about the file, such as the location of a buffer, the current character position in the buffer, whether the file is being read or written, and the like. User don't need to know the details, because part of the standardized natural definitions obtained from the edge is a structure definition called file. The only declaration needed for a file pointer is exemplified by this. This says that fp is a pointer to a file, and fopen returns a pointer to a file. Notice that file is a type name, like int, not a structure tag. It is implemented as a type div. Details of how this all works on the Unix system are given in Chapter 8. The actual call to fopen in a program is: the first argument of fopen is the name of the file as a character string. The second argument is the mode, also as a character string, which indicates how one intends to use the file. Allowable modes are read, write, and append. Hang on. If you open a file which does not exist for writing or appending, it is append. It is created if possible. An opening an existing file or opening an existing file for writing causes the old contents to be discarded. Trying to read a file that does not exist is an error, and there may be other causes of error as well, like trying to read a file when you don't have permission, when you don't have authority. If there's any error, fopen will return the null pointer value null, which for convenience is also defined in stu.h. The next thing needed is a way to read or write the file once it is open. There are several possibilities, of which getC and putC are the simplest. GetC returns the next character from a file. It needs the file pointer to tell it what file. Thus, places in C the next character from the file referred to by fp and uif when it reaches end of file. Put C is the inverse of get C. Puts the character C on the file fp and returns C like getChar and putChar. GetC and putC may be macros instead of functions. When a program is started, three files are opened automatically, and file pointers are provided for them. These files are the standard input, the standard output, and the standard error output. The corresponding file pointers are called sting, stout, and stir. Normally, these are all connected to the terminal, but sting and stout may be redirected to files or pipes as described in section 7.2. GetChar and putChar can be defined in terms of getC, putC, sting, and stout as follows. For formatted input or output of files, the functions fscanf and fprintf may be used. They are identical to scanf and printf, save that the first argument is a file pointer that specifies the file to be read or written. The control string is the second argument. With this preliminaries out of the way, we are now in a position to write the program cat to concatenate files. The basic design is one that has been found convenient for many programs. If there are command line arguments, they are processed in order. If there are no arguments, the standard input is processed. This way, the program can be used stand-alone or as part of a larger process, like these words. The file pointers sting and stout are predefined in the International library as the standard input and standard output. They may be used anywhere an object of type file asterisk can be. There are constants, however, not variables, so don't try to assign to them. The function fclose is the inverse of fopen. It breaks the connection between the file pointer and the external name that was established by fopen, freeing the file pointer for another file. Since most operating systems have some limit on the number of simultaneously open files that a program may have. It's a good idea to free things when they are no longer needed, as we did in cat. This is also another reason for fclose on an output file. It flushes the buffer in which putC is collecting output. fclose is called automatically for each open file when a program terminates normally. 7.7 Error handling. Stir and excite. The treatment of errors in cat is not ideal. The trouble is that if one of the files can't be accessed for some reason, the diagnostic is printed at the end of the concatenated output. This is acceptable if that output is going to a terminal, but bad if it is going into a file or into another program via a pipeline. To handle this situation better, a second output file called stir is assigned to a program in the same way that string is styled are. If at all possible, output written on stir appears on the user's terminal even if the standard output is redirected. Net has a revised kit to write its error messages on the standard error file. The program signals errors two ways. The diagnostic output produced by fprintf goes on to stir, so it finds its way to the user's terminal instead of disappearing down a pipeline or into an output file. The program also uses the standard library function excite, which terminates program execution when it is called. The argument of excite is available to whatever process called this one. So the success or failure of the program can be tested by another program that uses this one as a subprocess. By convention, a return value of 0 signals that all is well, and various non-zero values signal abnormal situations. Excite calls fclose for each open output file to flush out any buffered output, then calls a routine named _excite. The function _excite causes immediate termination without any buffer flushing. Of course, it may be called directly if desired. 7.8 Line input and output. The standard library provides a routine fgs which is quite similar to the getLine function that we have used throughout the book. The call, like this, reads the next input line, including the new line, from file fp into the character array line. At most max line -1 characters will be read. The resulting line is terminated with \0. Normally, fgs returns 9. On end of file, it returns null. Our getLine returns the line length and 0 for end of file. For output, the function fputs writes a string which need not contain a new line to a file. To show that there is nothing magic about functions like fgets and fputs, here they are, copied directly from the standard isnatural library. Sorry. Exercise 7 middle score 3. Write a program to compare two files. Print in the first line and character position where they Write a program to compare two files. Print in the first line and character position where they differ. Exercise 7 middle score 4. Modify the pattern finding program of chapter 5 to take its input from a set of named files, or if no files are named, its arguments from the standard input. Should the file name be printed when the matching line is found? Exercise 7 middle score 5. Write a program to print a set of files, starting each new one on a new page with a title and a running page count for each file. 7.9 Some miscellaneous 7.9 Some miscellaneous. 7.9 Some miscellaneous functions. The standard library provides a variety of functions, a few of which stand out as especially useful. We have already mentioned the string functions string, struct.py, struct.add, and struct.m. Here are some others. Character class testing and conversion. Several macros perform character tests and conversions. And getC. The standard library provides a rather restricted version of the function engage, which we wrote in chapter 4. It is called getC. Pushes the character C back onto file FP. Only one character to push back. Only one character of pushback is allowed per file, and getC may be used with any of the input functions and macros like scanf, getC, or getchar. System call. The function system executes the command contained in the character string S, then resumes execution of the current program. The contents of S depend strongly on the local operating system. As a trivial example, on Unix, the line causes the program date to be run. It prints the date and time of day. Storage management. The function clog is rather like the alloc we have used in previous chapters. Returns a pointer to enough space for an object of the specified size or null if the request cannot be satisfied. The storage is initialized to 0. The pointer has a proper alignment for the object in question, but it should be cast into the appropriate type, as in C-free frees the space pointed to by P when P is originally obtained by a call to clog. There are no restrictions on the order in which space is freed, but it is a ghastly error. But it is a ghastly error to free something not obtained by calling clog. Chapter 8 shows the implementation of a storage allocator like clog, in which allotted blocks may be freed in any order. Chapter 8. The Unix system interface. The material in this chapter is concerned with the interface between C programs and the Unix operating system. Since most C users are on Unix systems, this should be helpful to a majority of readers, even if you use C on a different machine. However, you should be able to glean more insight into C programming from studying these examples. The chapter is divided into 3 major areas: input/output file system and a storage allocator. The first 2 parts assume a modest familiarity. The first 2 parts assume a modest familiarity The first 2 parts assume a modest familiarity with the external characteristics of Unix. Chapter 7 was concerned with a system interface that is uniform across a variety of operating systems. On any particular system, the routines of the standard library have to be written in terms of the international facilities actually available on the host system. In the next few sections, we will describe the basic system entry points for international on the Unix operating system and illustrate how parts of the standard library can be implemented with them. 8.1 File Descriptors. In the Unix operating system, all input and output is done by reading or writing files, because all peripheral devices, even the user's terminal, are files in the file system. This means that a single homogeneous interface handles all communication between a program and peripheral devices. In the most general case, before reading or writing a file, it is necessary to inform the system of your intent to do so, a process called opening the file. If you are going to write on a file, it may also be necessary to create it. The system checks your right to do so. Does the file exist? Do you have permission to access it? And if all is well, returns to the program a more positive integer called a file descriptor. Whenever international is to be done on the file descriptor is used instead of the name to identify the file. This is roughly analogous to the use of read and write in Fortran. All information about an open file is maintained by the system. The user program refers to the file only by the file descriptor. Since input and output involving the user's terminal is so common, special arrangements exist to make this convenient. When the command interpreter, the shell, runs a program, it opens 3 files with the file descriptors 0, 1, and 2 called the standard input, the standard output, and the standard error output. All of these are normally connected to the terminal. So if a program reads file descriptor 0 and write file descriptors 1 and 2, it can do terminal international without worrying about opening the files. The user of a program can redirect international to and from files with, in this case, the shell changes the default assignments for file descriptors 0 and 1 from the terminal to the named files. Normally, file descriptor 2 remains attached to the terminal, so error messages can go there. Similar observations hold if the input or output is associated with a pipe. In all cases, it must be noted the file assignments are changed by the shell, not by the program. The program does not know where its input comes from nor where its output goes, so long as it uses file 0 for input and 1 and 2 for output. Okay, guys, it's time for me to take a break. Goodbye. See you.